Hello everybody, I am Alex Surnov, a biologist. Welcome to my course on mathematics and biology. Today is our second lecture. Previously, I discussed in detail the reasons why I decided to record these lectures, the importance of mathematics and biology, and the way how to explain mathematics to the listeners who need it but have never studied it in detail. For this, please review my first lecture, which is fully dedicated to the philosophy of mathematics and to the structure of the current course. Today's lecture, as well as a couple following lectures, will not contain any biological applications, but rather will introduce you to the necessary basic mathematical concepts. It is titled Real One-Dimensional Calculus. The word real here does not have anything to do with the concept of reality as such, it is just a mathematical term. Essentially, we are going to talk today about numbers and functions. Numbers are the objects that first come to mind once mathematics is mentioned, I hope. And functions are also very common mathematical objects, both very much prevalent in the theory and very useful for practical applications. Real one-dimensional calculus is usually explained very early in mathematical, technical or natural science colleges. Therefore, you are welcome to skip the current lecture if you already have the appropriate background. However, if you have no such background or have forgotten most of this science, then I sincerely encourage you to watch this video. If some of its parts seem too lengthy for you, do not hesitate to run it at the double speed. Alternatively, if you feel exhausted after a certain time, feel welcome to pause the talk and return to it later. As I have said, today's topic is rather basic. This is why I don't recommend you any particular literature for it. Virtually any calculus book will be appropriate for clarifying the undiscussed aspects. Do not ignore very old textbooks. Unlike in natural sciences, discoveries in mathematics are disproven extraordinarily rarely. So even books published in 1960s or in 1930s are safe to use. The information there may be incomplete, but it is never wrong. And in particular, everything related to basic calculus is illuminated there completely. As one example, I refer you to the very famous textbook by Courant, C-O-U-R-A-N-T, and John. John is the surname. I also encourage you to give me any feedback in YouTube or per email, send a like to this video, share it, or subscribe to the channel. On this, the introduction is over, and let's start with the lecture. Before going towards the theory, let's first agree on some notations. This flipped letter A-like symbol stands in mathematics for the phrase for each. So, for example, if you have a statement A and you want to emphasize that the statement A holds for each input number n, you simply write this for each symbol, then n, and then write that A holds. Similarly, the flipped letter E-like symbol stands for exists. If you want to emphasize that X exists, you just write this. You can use the negation symbols by just crossing the respective symbols out, and this, for example, stands for does not exist, and the equality sign crossed stands for not equal. The bold arrow facing rightwards stands for logical implication. For example, if there are two statements A and B logically follows from A, you just write that A implies B. The equality sign with the letters D, E, F above it stands for the equality by definition. For example, if you introduce the number C as the sum of A and B, and you want to emphasize this introduction, you write that C by definition equals to A plus B. However, sometimes this equality sign by definition can be just replaced with regular equality sign if it's understandable from the context. Now the strange symbol that looks like a rounded E, whatever, stands for belongs. If you have a set S capital, and X is the elements of S, it says X belongs to S. This symbol stands for X belongs to S. Additionally, there are some symbols that are the relatives of the previous one. For example, this symbol here stands for being a subset, and a set that contains only X and Y, while both of them being the elements of S, is called a subset of S, and this horseshoe-like symbol just designates that this smaller set is a subset of the bigger set. The two flipped horseshoe symbols stands for set intersection and set union, and here is the intersection and here is the union. And finally, the bold letter N stands for the set of all natural numbers, and the natural numbers are those that we can count with. It's 1, 2, 3, 4, etc., all the way to infinity. It's the numbers that we can use for counting separate, indivisible objects. All right. Once the notations are clear, let's move to the first scientific concept that we wanted to discuss, and this is going to be a concept of a real number. The term real here is a strict mathematical word. It has a particular meaning to it, and later we will separate the numbers that we call real from some broader class of numbers for which other terms are used. But I think this will happen just in the next lecture, not here. For now, the real numbers cover all the numbers that we will deal with. Okay, so a non-negative real number is just a sequence of digits and a decimal separator. The digits are those objects that we study at first grade of a school, and namely it is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, nothing else. Those just these 10 symbols. And the decimal separator in most of the world is a comma. However, in the United States is a dot, a period. So it is a potentially infinite sequence. There is a finite number of symbols to the left from the decimal separator, always finite. Without loss of generality, I indicated here just one. And a potentially infinite tail of the digits to the right from the decimal separator, with one caveat, with one convention, that if after a certain position there are going to be only 9s, then such a number is by definition claimed to be equal to its modified form, to another number, to the number where the last non-9 the last digit before the infinite 9 tail gets an increment of 1, and the rest of the digits are claimed to be 0. So if you have like 1, 2, 3, whatever, 8, and then 9, 9, 9, 9, 9, all the way to infinity, it's just going to be the same as 1, 2, 3, boo, 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 8 plus 1, namely 9 here, and then zeros. And of course, the researchers agreed that the tail that consists of only zeros can be omitted, because why on earth would we write infinite number of zeros, right? So that was the non-negative number. And the negative number is just the same, but with the minus sign written to the left from it. And obviously 0 is the number that consists of all zeros. Now the set of all real numbers is denoted by a bold letter R, and apparently it's the union of all non-negative numbers, all negative numbers, and the zero. One can do certain procedures with the numbers. For example, one can compare them. Assume there are two numbers, alpha and beta. Alpha consists of the digits named m with indices, and beta consists of the digits n with indices, and all they are non-negative. These two numbers are non-negative. How to compare them? How to decide which one is greater? Well, assume at least one of the two following statements holds. First of all, the integer part, the part that is located to the left from the decimal separator of the number alpha, is smaller than the integer part of the number beta. And by integer parts, I mean those parts that are located to the left from the decimal separator. That's one condition. Or they are equal to each other, the m0 and n0. However, in this case, there exists such a position k that the digits in alpha and beta are all equal in the corresponding positions all the way before k. However, at the position k, the corresponding digit of alpha is smaller than the one of beta. And if either of these conditions holds, this means by definition that alpha is smaller than beta. Once again, under the constraint that both are non-negative. And here is the example. The integer parts of alpha and beta is the same, it's 5. The first decimal digit is the same, the second is the same. However, the third one is smaller in alpha than in beta. And then we conclude that alpha is smaller than beta based on the second condition of our definition. For the negative numbers, if alpha and beta are negative, then the number negative alpha and the number negative beta are positive. And in this case, if the negative alpha is greater than the negative beta, then by definition we say that alpha is smaller than beta. For the numbers of different sign, negative numbers are assumed to be always smaller than the positive ones by definition. Here, we can introduce one example of a theorem. It's a very simple theorem, and don't worry, I'm not gonna bother you with lots of formal derivations of statements with formal proofs and with like more details about upcoming theorems. I am giving the current one here just in order to show you the general mindset of mathematicians when they prove something, when they derive their statements. I want you to appreciate the thoroughness of their thoughts as illustrated in this very simple example. So here is the theorem. The statement is, for every alpha that is smaller than beta, for every two numbers, alpha and beta, such that alpha is smaller than beta, there always exists another number, gamma, such that it is greater than alpha but is smaller than beta. In other words, for each two numbers there exists the third one that lies between them. And let us prove it. So write down alpha in the above mentioned form and beta as well. Assume they are non-negative first, and assume they don't have the all 9 tail, which we have already discussed above. Let's find the first decimal that is difference between them, and we know that it is possible to do based on what we already learned. So may m naught equals n naught, m sub 1 equals n sub 1, and so on, all the way till the position k, where m sub k is smaller than n sub k. At least one of the following decimals in alpha, starting from m sub k plus 1 and then to infinity, is not 9 by condition. Here is the condition. So for example, may that be m sub k plus l, that is non-9. Then construct the number gamma the following way. We keep all the digits from alpha up to the position m sub k plus l minus 1, and we give the increments of 1 to the digit of alpha standing in the position of m sub k plus l, which is not 9 as we just agreed. It's easy to check in this case that gamma is indeed greater than alpha and smaller than beta. How do we check it? Well, for example, there are two numbers, this and this. We found the digit that is responsible for alpha being smaller than beta is the digit that is 4 here and 7 here in the corresponding position. We find an arbitrary digit after it, which is non-9, and may it be this little one here, which is labeled in blue. And then we give the increments of 1 to it, and we shrink the gamma from it. So we claim that all the rest of the digits in gamma are equal to 0. Essentially, we constructed gamma this way. We copied all the digits from alpha until the 1. We converted the 1 to the digit 2, and we truncated the tail of the digits that would follow it. So we made it just all zeros after the 2. And then what can we say about this gamma? It is indeed smaller than beta because it inherited all the digits before this position, and in fact it also inherited the digit that is 4 here and 7 here, which makes the gamma to be smaller than beta just because of these red digits here. But also gamma is greater than alpha, again because it inherited all the digits from alpha up to the position that is marked in blue, and the position that is marked in blue is occupied by the digit 2 in gamma, but in alpha is just 1. And the tail here in alpha is not all 9, so we just cannot convert this 1 to 2. There is no convention for it. And yeah, so that's how the gamma is greater than alpha, based on this difference between 1 and 2, and that's how gamma is greater than beta based on the difference between the 4 and the 7. And for the negative numbers, the proof is just analogical. They are symmetric to the non-negative numbers, And if one number is negative and another one is positive, then there is always going to be 0 between them. So this reasoning completes the proof. And here I just want to pronounce it once again, that every mathematical statement must be formulated so clearly that no listener or reader would have any doubts about it. Every logical step is, is explicitly implied by the previous ones. There is no ambiguity, there is nothing untold, there is nothing accepted by trust, and everything is extremely, ultimately, solidly grounded. That's the way how mathematicians prove their theorems. That's the way how they think. They just formally deduce next statements from the previous ones and eventually from the axioms. A very important concept is the duality between all real numbers and a straight line. And the line is called the real axis. So let's draw a straight line and let's fix 2 points there. O stands for origin and E stands for, well, unity, I guess. The distance between them by definition is said to be 1. And given this construction, there is a way to represent every real number as a segment on this line and every segment as a real number. So for example, let's examine the real number 3.46, and the rest of the digits are all zeros. So what does it mean? It corresponds to the segment that is as long as the 3 unit segments taken together, followed by the 4 segments 10 times shorter than the unit one, followed yet by 6 segments that are 100 times shorter than the unit one. 3 plus 4/10 plus 600th. And obviously, if we mark another point, so making just another arbitrary segments on the line, this segment will also correspond to a certain number using the same convention. Actually, there is a notation. The A and B embedded in the rectangular brackets just denotes a segment if the ends of the segments are included. However, if the brackets are flipped like this, it also denotes the segment, but it's an open segment or an interval. It's essentially a segment in which its ends are not included, so only the interior of the segment. Sometimes some authors use round parentheses instead of the flipped brackets, but I think the flipped bracket is a valid notation too. At least I got used to it. The duality between the line and the set of real numbers allows us to examine the concepts of rational and irrational numbers. As written here, the numbers whose decimal tail is periodic after a certain digit is called irrational. And one can prove that such numbers are representable as a ratio of 2 whole numbers, the numbers without the decimal tail, numbers that consist only of the integer part. And here are the examples. So the real number that is written as 0.733333 and so on does have this periodic tail that consists of threes, only three, and as implied by the theorem, as stated by this theorem, it is representable as a ratio of two whole numbers, which are in this case 11 and 15. The number 0.25 also has this periodic tail of zeros that we agreed not to write down, and obviously it is a ratio of 1 and 4. The other numbers are irrational. And don't worry, the term irrational doesn't mean somehow, it doesn't have anything to do with being wrong or incorrect or counterintuitive, whatever. No, irrational is just every real number that is not rational, that cannot be represented as a ratio of whole numbers. And the irrational numbers are not representable as the ratio of two whole numbers, as it's said here, as I just said. Sorry, I just didn't read actually this line before saying it verbally. The real numbers, all real numbers, are the union of all rational and all irrational numbers. And actually, we have proven that there exists a rational number between every two arbitrary numbers. That number gamma that we constructed to sit between alpha and beta 2 slides before has that periodic tail of zeros, and therefore gamma is rational. The set of all rational numbers is denoted as the bold letter Q. An example of an irrational number is the square root of 2. Imagine a square whose sides are all equal to 1 in length. Then its diagonal equals to square root of 2 based on the Pythagorean theorem, right? Pythagorean formula. And one can prove that the square root of 2 is irrational, namely, you never will stop the sequence of those segments when trying to approximate the square root of 2 by the sequence of the segments. So you fit one time the unit segment in this number, you fit in addition 4 times the segments whose length is 1/10 of the unit into this segment. Then you try to fill this little gap with one more segment that is yet shorter, 100 times shorter, but there is still going to be a little gap. You will try to fill this gap with the units, with the segments whose length is 1/1000 of a unit, and you still will have yet smaller gap, and so on and so on. So you will keep filling these little gaps with more and more shorter and shorter segments, but you will never be able to fill it ultimately. A certain gap will always remain, and the sequence of those digits will never be periodic. There is not going to be a pattern that repeats strictly starting from a certain point. This statement is not so hard. It's pretty easily provable but it relies on a theorem which we haven't yet discussed and which we actually will not discuss or use later in this course. Therefore, I'm not giving you the proof right here. Everyone who is curious about the proof, you're welcome to read the corresponding Wikipedia article. It is pretty well described there. Not a big problem. Real numbers within their real axis can be organized in certain sets. And the sets also have their own properties. For example, they have supremum and infimum. Assume x capital is a subset of all real numbers. Then its supremum is such a number a, denoted as sub of x, such a number that the two following conditions hold simultaneously. First of all elements of x must be smaller than or equal to a. And secondly, in every neighborhood of a, even an arbitrarily narrow neighborhood, there must exist at least one number that belongs to x. And the infimum of x is defined symmetrically with the difference that here must be the words greater. Sorry, here there must be the words greater, not smaller. And that's it. That's the only difference. And here are the examples. There are three sets. We see that the first set is a segment, and it does have a supremum, namely its rightmost end is the supremum, because every element of this segment is smaller than or equal to it, and in every neighborhood of this point, there are points that belong to the segments. No matter how small neighborhoods we restrict here, there is always going to be a small portion of the segment that is adjacent to the end. Here is another example of a set. It's the set of equally spaced points on the real axis which go all the way to infinity. And obviously there is no supremum to this set, because there is just simply not such a number. All elements of x would be smaller than or equal to. There is just not. It's unbounded. This set is unbounded. There is not going to be a number that satisfies the condition 1. Another example is a bit more tricky. It also contains some discrete dots. It consists of discrete dots, but the distance between these dots becomes smaller and smaller, and eventually the infinite number of these dots is aggregated around a certain point. They're all discrete, but they are nonetheless just clustered and compactified around a certain position. And therefore there is also a supremum here. However, this supremum is not a member of the set anymore. It doesn't belong to the set. It is a certain point on the real axis around which the dots are aggregated denser and denser while remaining discrete. So these three examples show us the three possible types of behavior. The supremum or infimum can be either the member of the corresponding set itself, or it may not just exist, Or alternatively, it may exist but not being a member of the set. Why do I pay so much attention to those supremum and infimum things? They seem too boring and for sure not related to biology anyhow. However, I introduce them because they allow us to strictly define the arithmetical operations over the real numbers, since we are motivated to be precise and we are motivated to think the way mathematicians think. I cannot just simply say that real numbers can be added to each other or subtracted from one another. We need to formulate those operations absolutely strictly. And for this, as I said, the supremum and infimum are necessary. So the operations. One can do several things with real numbers. One can compare them, as we just discussed, but also one can define the arithmetical operations. And for rational numbers, they are trivial, those operations. One can add, subtract, and multiply rational numbers just using the school rules. However, for arbitrary real numbers, the arithmetical operations are a bit more tedious. They are strictly defined as the supremum of the corresponding operation outcome of taken for the rational numbers that approximate the original numbers. So alpha plus beta, if alpha and beta are arbitrary real numbers, is by definition said to be the supremum of x plus y, where x and y are both rational, and we know how to add them since they're rational. And in addition, x is smaller than alpha and y is smaller than beta. Here is the example. We have two infinite sequence of digits, two real numbers, alpha and beta, and we approximate them by truncating those tails to the first digit, to the second digit, and computing their sum, the sum of rounded alpha and beta, the sum of alpha and beta that are rounded more precisely, the sum of alpha and beta that are rounded yet more precisely, and so on. And the behavior of this set of approximations is just the same what we saw on the previous slide. It aggregates more and more around a certain value, which is by definition the sum of alpha and beta, and which is the supremum of the set of the approximations. Similarly, one can introduce the subtraction, multiplication, and division, but the division is defined only if there is no zero in the denominator. No one can divide by zero. All right. I guess that's all about the numbers that we want to know so far. Let's move to another very, very important concept, namely the functions. And the table of contents grows here, which will help you to navigate through the presentation. So the functions, well, almost everything in mathematics is formulated on the language of functions, honestly speaking. Therefore, it's extremely important to understand them. What the functions are? The functions are mappings. The functions are mappings, these are rules, these are transformations of sets of numbers. May x capital and y capital be the subsets of real numbers. Then the function f that maps x capital to y capital is such a rule that assigns a certain elements of y to each element of x. So, for example, if there is an element of x capital that is called x small, the function f assigns the element y small of the set y capital to this element. It's a mapping. It's a mapping that sends x to y. And more so, it is an unambiguous mapping, meaning that every x is allowed to be mapped to only one y. Several different values of x can be mapped to the same y, but no element x is allowed to have more than one images. That's it. Very often, the functions are depicted or illustrated as their charts. What do I write here? What is written here? This is just the same as before. So, for example, let's draw a real axis and another real axis orthogonal to it. And then for every element of the first real axis, or for every element of the subset x capital of the first real axis, we mark this point and we mark the points of its image to which the function f sends this elements of x. So here is a trivial example. The function just assigns the same number to every number. Both x capital and y capital are just the whole real axis, and the mapping just doesn't do anything particular. It really assigns the same number to each number. And the chart of this function is a straight line diagonal to the angle between those two orthogonal lines. And we see that to the number x equals to 2, it gives the corresponding number y equals to 2. The number x equals to 4, it sends to y equals to 4, and so forth. A more interesting example is the function that maps x to the number x plus 3. Its chart is also a straight line, but it's shifted. It maps the x equals to 2 to y equals to 5, and x equals to negative 2 is mapped to y equals to 1. You can just imagine other formulae. For example, here y equals to 2x. It is represented by another chart where 4 is corresponding to 2 and negative 4 is corresponding to negative 2. Not every function has a chart that is representable as a straight line. For example, here in blue, there is the chart of a function that is equal to 1 over x. In this case, the domain of definition x capital is the whole real axis without 0, as well as the domain of possible values is the whole is the whole real axis without 0. And the chart of this function, 1 over x, is hyperbolic. it tends to 0 as x approaches positive or negative infinity, and it diverges around the 0, which illustrates that no one can divide by 0. Obviously, it sends x equals 2 to 0.5, and it sends x equals to 4 to 0.25. And here are the modifications to this function the same way as we did it here. X is, how to say it, y equals to 2 over x in gray, and y equals to 1 over x plus 3 in orange. Not all functions are so easily visualizable. Some are pretty bizarre, but those are rather exotic, and they do not appear in regular life that often. But for example, just for the completeness of the picture, there is such a function called Dirichlet function, and Dirichlet is the surname of the researcher who invented it. And what does this function do? It maps every rational number into 1 and every irrational number into 0. Given that rational and irrational numbers are infinitely densely intermixed within the set of real numbers, there is no way to depict this function precisely. Its chart will consist of an infinitely dense collection of points at 0 and an infinitely dense collection of points at 1, which is obviously impossible to depict precisely. Yeah. But one can think about this function, one can operate it mathematically, one can draw an approximate graph like this. So it's not a big deal if you cannot draw a graph. It's not preventing you from thinking about the functions and from using them and from analyzing them strictly. Some simple arithmetical transforms affects the plots in a particular way, in a strict way. So, for example, if there is a function with such a chart, multiplication of its arguments by a certain constant factor will just shrink the chart with respect to the length. I mean, shrink it around the vertical axis. And by saying in arguments, I mean the x value in the parentheses, the the points in which the function is computed. If you multiply the output of the function by a constant factor, this will result in stretching the chart with respect to the horizontal, or around the horizontal axis, as written here. If you give an increment, a negative increment to the argument, a constant negative increment, it will result in the shift of the chart rightward. Respectively, if the increment is positive, it will shift the chart leftward. And finally, if you multiply the argument, sorry, I'm recovering from common cold. My voice is not as strong as I planned it to be. If you multiply the arguments of this function by the factor of -1, it will flip the chart around the vertical axis. And also here, there is an illustration that it's a valid behavior for the function when a certain value of y corresponds to more than one values of x. So for example, y equals to 0 corresponds to this x and this x and this x simultaneously. What is not allowed for the function is not allowed the situation when one x has more than one y. So for example, if this line would bend here downwards and leftwards, and at some points we would find two different values of y for the same x, then we would say no, it's not a valid function. It's another mathematical object that we can deal with, and we know how to formulate it and work with it, but it's not a function in its strict meaning. However, such a behavior is completely valid for a function, and we have no problems with that. So we just learned the arithmetical transformations of the functions and their arguments, and next comes yet one more useful transformation that we can do with some functions. It is the inverse. Assume that the function f of x maps the set x capital into the set y capital unambiguously in both directions, meaning that there corresponds only one value of y to each value of x. Then, obviously, there exists the function g of y that is inverse to f, such that the function g computed at the points f of x equals to x, and the function f that is computed at the point g of x is also equals to x. So the effect of g compensates the effect of f made on x. So these functions are mutually inverse to each other, and let's see how to construct a chart of an inverse function based on the charts of the original function. So if f is an unambiguous mapping, then its chart is monotonous. It doesn't have it doesn't have peaks or wells. It always either grows or descends over the domain of definition capital X. And in order to construct the charts of the inverse function from this chart, you have to imagine the chart being printed on a sheet of paper, and then you gently grab the upper left corner of this chart and flip it just the way depicted with those arrows. You start looking at this sheet of paper from its rear side, so you flip it upside down, and you also turn it by 90 degrees. So this corner here goes here, and this left upper corner goes down here. The resulting chart is going to be also monotonous, and the function is going to be the inverse of the original one. So we're progressing further and further through our table of contents, and now we're approaching another big section of our presentation, which is called limits. And we start the examination of limits by studying a finite limit at infinity. Assume the function f of x is defined for all values of x greater than a certain fixed points a, as shown here, its domain of definition is infinite on one its side, then one can say that a certain number c equals or is a limit of the function f of x when x tends to positive infinity, if and only if the following condition is satisfied. For every arbitrarily small number epsilon greater than 0, there exists the number b greater than a, such that for every x that is greater than b, the following property is satisfied. The distance between f of x computed in this point and c is smaller than epsilon. How to interpret this convoluted line? What does it essentially mean? Well, it means a very simple thing. It means that c is such a number to which the function f of x tends as x grows. So, for example, we suggest that the number 2, c equals to 2, is the limit of the function f of x. And let's probe it. Let's check whether the c is indeed the limit. What can we do? We choose an arbitrary positive number epsilon, and we create the neighborhoods with radius epsilon around the number 2 or the number c. And then we check whether there is such a number b existing that for every x that is greater than b, the value of f of x will lie within this neighborhood here. And the answer is yes. Here is the b. For every x that is located to the right from b, the values of f of x are all sitting within the neighborhoods of the radius epsilon taken around the number c. If we take a smaller value of epsilon, for example, twice smaller than the one shown here, well, then we again will be able to find such a b, probably somewhere here, after which all the values of f of x will be confined within this neighborhood, and so on. No matter how small we choose the epsilon to be, there always will be a certain b, the certain value of b, after which all f of x values will be confined within the neighborhood of c. Moreover, such a procedure will not work for any other number than 2 in this case, or than this c. Assume we choose c that equals to 1.5. Then for certain epsilon values, the values of f of x will exceed the borders of these neighborhoods, and the following rule will not be satisfied anymore. This one, the one that I'm showing with a pointer. The functions do not, even like the functions that do have limits at infinity, they do not have to tend to these limits from one side only. For example, here is the function that oscillates periodically around the limits, but the magnitude of these oscillations is smaller and smaller and smaller, and also tends to 0, and the function itself tends to the limits anyways. It is a valid behavior as well. The main idea is that the magnitude of these oscillations must be approaching 0 as x grows. So that's the limits at infinity. Now let's examine a finite limit at a point. Its definition is similar. Point C, or a value C, a number C, is called to be a limit of the function f of x as x approaches a fixed point A, if and only if for every arbitrarily small positive number epsilon there exists a positive number delta such that for every x that belongs to the delta neighborhood of A with the point A itself being excluded, the following property holds. The distance between f of x and the C is smaller than epsilon. And just the same as on the previous slide, we have this function here. We fix the point A. We want to probe whether the value C is the limits of this function as x approaches A. What do we do? We choose the epsilon neighborhood and we check if there is a number delta such that for every x that belongs to this delta neighborhood of the points A, except probably or possibly except for letter A itself or the number A itself, the values of f of x will be confined within the epsilon neighborhood of C. And the answer is yes. This delta neighborhood of A is depicted here by this shaded orange pinkish color. And f of x is all contained within the epsilon neighborhoods as long as it's computed in this neighborhood, delta neighborhood of A. We shrink the epsilon, the delta will be shrunk too. We shrink epsilon more, the delta will be shrunk yet more. But the property will hold for every f of x within the delta neighborhood of A, maybe except for A itself. And here is the example of why I'm saying maybe because of A itself. Well, because here in this graph, the value for the limit is pretty trivial. It is just the value of the function itself computed at the point A. And you may wonder, why do we need such a long definition for a concept which is so simple? In order to compute the limits of this function in the points A, you just simply have to compute the value of this function. But there are some other situations when this definition may be crucial. So let's draw once again this picture here. Here it is. The value of the function f of x computed at the point A is just equal to its limits as x approaches to A. Such functions are called continuous. Continuous at the point A. A small deviation from A along the x-axis causes also small change in y. That's an informal concept of continuity. And the formal definition of being continuous at the point A is here, when the limit is equal to the value of the function in the given point. However, we can modify our function just by definition, keeping all the values except for the value in the point A. And in the point A, we can artificially define the value of the function being different from its limit. and then the function is not longer continuous, it's called discontinuous in this case, because certain small increments within the neighborhoods of the points A may result to a greater leap in the value of the function. So we started from somewhere here, we made a tiny increment to x, and hoping that the function will change also mildly, just the way how it was in the upper chart, but we accidentally hit the point A itself, at which the function just catapults us upwards to these artificial points here. So that's discontinuity. The limit is not longer equal to the actual value of the function. Here is another example of discontinuity when the limit is not even equal to a certain finite number, but is equal to infinity. As we approach to the point A, the function starts growing unlimitedly, as shown here in this line. For example, such behavior appears when the function is represented as a ratio and the denominator vanishes and the numerator is non-zero. So that's the infinite limit at a point, and also there can be an infinite limit at infinity, meaning just simply that the function grows unlimitedly, unboundedly, as x grows too. Sometimes mathematical strictness may be funny, and here are good examples of that related to the concept of limits. So there are two theorems proven about limits, and they are pretty simple. They are also taught in the first year of college or in mathematical calculus, whatever. But they seem on one hand very obvious, on the other hand mathematics are like so precise and so formal that they need to deduce them strictly. So one statement is the following: if the function grows monotonously and is bounded from above, then it has a finite limit at x when x tends to infinity. And once again, it's from the geometrical point of view, it's an obvious statement. Here is a monotonous function. It always grows, but it can never grow above than a certain boundary depicted here in gray. So obviously there must be a limit. However, once again, there is a proof for it, and this proof is not that trivial, so to say. It requires some reasoning and some thinking. Another statement: if the function is continuous everywhere on a certain segment with its endpoints as well, and has different signs on its ends, then there exists such a point within these segments at which the function vanishes. And again, an obvious statement: if you imagine the chart of the function as a continuous rope or a lace, and it is located below the x-axis on one end of the segments and above the x-axis on the other end, obviously it must cross the x-axis at some point, maybe multiple times as shown here. But once again, there is a formal proof to this statement. Now let's have a look at the examples of functions, and we'll start with trigonometric functions. We all know what sine and cosine is for a given angle x. So for example, let's draw this circle of the unit radius, and let's call the angle between the horizontal axis and the radius of this circle as x, then the cosine of x is nothing more than just the length of the projection of these points here to the horizontal axis, and the sine of x is the length of this vertical projection. And from Pythagorean formula, it's obvious that sine of x squared plus cosine of x squared must be equal to 1, because the radius of this circle is 1. It's just the Pythagorean formula, nothing else. However, we can represent the sine and cosine as functions of x when we rotate this radius around the origin more and more, and for every value of x we write down the values of sine and cosine. And the behavior of the function is going to be this. We start at x equals to 0, meaning that this radius is just coincides with the horizontal axis, and then x starts growing by turning the radius counterclockwise, and we see that cosine of x just becomes smaller and smaller and vanishes when x reaches 90 degrees, when it stands vertically, while sine of x, this length of this projection, starts at 0 and then reaches 1 when x becomes 90 degrees. Here I measure x in different units. I measure in degrees or in fractures of pi, which is the same. Pi over 2 is the same as 90 degrees, and pi itself is the same as 180 degrees, just different scales of measurements, like miles and kilometers. Just one can be converted to each other. They can be converted to each other. So we have two functions. They both are periodic. They repeat after every time after the 2 pi is over, after x completes one whole revolution. Now, what can we do with these functions? Well, we can apply some arithmetical operations to them. For example, we can divide one by another and create a tangent function. Here it is. It is equal to sine divided by cosine. And since cosine is almost equal to 1 when x is small, when x is around 0, the value of tangent is almost equal to sine itself when x is computed around 0. However, when x approaches pi over 2 or 90 degrees, cosine vanishes as shown here, and tangent just diverges. It behaves the same way as 1 over x. Here and here and in every point where cosine vanishes, because you cannot divide by 0. We already know that if you divide something by 0, something non-zero divided by 0, the result will diverge. We also are pretty tempted to compute the inverse of sine and cosine, but there is a caveat. These functions are not two-way unambiguous. They map several different values of x to the same y, and they have wells and peaks. Therefore, we cannot construct the inverse function that is valid for all values of x. However, we can subset the original functions restrict them to a particular segment on which they are monotonous, they are mutually unambiguous on both sides, and then use only this constraint function to compute the inverse one. And here is the example, or the illustration, I should say. The blue line represents the inverse sign. It is computed only for the original values of x that belong from negative pi over 2 to positive pi over 2, and the original values belong from negative 1 to 1. The orange is the inverse cosine, and the gray is the inverse tangent. So these functions are derived from just one branch or one segment of the original functions, subsetted functions. Now, okay, so that's the trigonometric functions. It's important to know them. It's useful to just memorize them, to know how they behave, but obviously they don't exhaust all the variety of functions that mathematicians operate and the variety of functions that you may face during your biomathematical research or in mathematical books. Let's proceed with other examples of functions. I will show you how they behave as well. Powers. Well, for an arbitrary number x and a natural number n, the power, like the x to the power n, is nothing more than just the product, x times x times x n times. The ax raised to the inverse power, inverse natural power, 1 over n, is the nth root of x. Why? Well, because we need the composition rule to be preserved. The composition rule is x raised to the power n, and then yet once again raised to the power k must be equal to x to the power n times k. And if we want this to hold for the function x to the power 1 over n, we must admit that this function is just the inverse of this function, and therefore it is the nth root of x. Okay, so we know how to raise x to the nth, to the natural power and to the inverse natural power. And this means that by using this composition rule, we can compute any rational power. X to the power k over n equals nothing more than just x to the power k raised yet again to the power 1 over n. If x is meant to be raised to an arbitrary real power, an irrational power probably, then this operation is defined via supremum, just the same way as we introduced the addition and multiplication previously. The existence of such supremum has to be formally proven, and it is proven. There are theorems for it. X to the negative natural power, x to the power negative n, is just the same as 1 over x to the power n for positive x. Why? Well, again, because we need another composition rule to be preserved, namely the product of x to the power k and x to the power n must be equal to x to the power k plus n. And if we want this rule to hold for this function, we have to admit that the function x to the negative n power is just the same as the inverse sorry, is just the same as 1 over x to the power n. All right, so now if a is a whole number with any sign, not necessarily positive, then x to the power a is defined as negative 1 to the power a times the absolute value of x to the power a for x of arbitrary sign as well, as depicted here. So for the positive values of x, x squared is this half of the parabola here. And for the negative x, x squared is also defined as this branch of the parabola. It's the negative 1 to the power 2 times the absolute value of x, which is negative for negative values of x here, also raised to the power 2. In case of the cubic curve, for the positive values of x, it's this branch, and for the negative values of x, it's negative 1 to the power of 3, which will be negative 1 times x cubed, or the absolute value of x cubed. For the whole numbers a, integer numbers a of any sign, this can be computed as well. And generally speaking, for positive values of x, the power functions have the following shape. If the exponents of the power is greater than 1, then it's more or less the shape of parabola. If, as shown here in the gray curve, if the exponents of this power, the number here, is greater than 0 but smaller than 1, then the function has, or the chart of the function has approximately the shape of the square root, or like nth power root. And if the exponent is negative, then it behaves roughly like a hyperbola. It diverges as x approaches 0, and it tends to 0 when x grows, as shown here in the blue line. Powers are, how should I say it? Powers are extremely powerful. I guess it's a good phrase. They are useful. The power functions are useful to compute polynomials, and polynomials are playing such a great role in all mathematics that it's hard to overestimate their role. And we will talk a little bit about the polynomials right now, and further we definitely will talk pretty much about the applications of them. So polynomials. Polynomials are just the sums of different powers of x with certain coefficients, as shown here. The maximal exponent, the number n here, a natural number n, is called the order of the polynomial. And the coefficients here are just arbitrary real numbers. Polynomial functions have the following properties. First of all, if the order of the polynomial is even, this n here, then the whiskers are pointing to the same direction. As shown here for the polynomial of the fourth order, its whiskers are both pointing upwards, or maybe they may be pointing downwards as well. It depends on the sign of these coefficients here. If there was a polynomial of third power, as in the previous slide, for example, then one whisker would point downwards, another one would point upwards at infinity. By whiskers, I mean those those branches that go to infinity. The second property, the behavior of this function at positive and negative infinity is defined by the most superior summand, a sub n times x to the power n, this one. What does it mean? Well, it means that if the absolute value of x is very large, if x goes all the way here or there to the left, then the value of the function f of x will be approximately equal to just the value of this expression here, a sub n times x to the power n. All other summands are irrelevant for such huge values of x. However, if x is not very large, other summands can play a significant role too. The property number 3, between the whiskers, the plot, the chart, can change its direction at most n-1 times. So that's a fourth order polynomial. Let's see how many times it changes its direction. 1, 2, and 3. Okay, at most n-1, maybe less than that. At most n-1. Number 4, there can be at most n points where the polynomial function vanishes. And here there are n equals to 4, and there are 4 roots. 1, 2, 3, 4. There may be fewer, but at most 4. And finally, it's very tempting to compute the roots based on the coefficients a0, a sub 1, and so on. But only for n equals 2, there is a simple formula that expresses the roots using the coefficients and the elementary arithmetic operations. Namely, here it is. The formula that computes the roots of a quadratic polynomial, second order polynomial, from its coefficients. Such similar formulae exist for n equals 3 and n equals 4, and they are called Cardano and Ferrari formulae, but they are way too bulky to be used in general practice. And the most sad result in this aspect is that there is no universal root formula for n which is greater than 4. So it's impossible to compute, in general case, the roots of the of a fifth order polynomial based on just its coefficients and using summation, subtraction, multiplication, and division, and computation of roots. No way. It's Galois theory, and it's strictly proven. So numeric algorithms are used, and they are pretty efficient. Approximate numeric algorithms, they are saved as certain computational tools in computers and software packages and stuff. Another example, an exponential function. It grows a times every time the argument gets a unit increment. So it's formulated as a number a to the power x. It grows extremely fast. It grows a times at every unit increments of x as x approaches positive infinity, and it vanishes the same fast as x approaches negative infinity for a that is greater than 1. For a that belongs to the segment or to the interval between 0 and 1, the function a to the power x is just the same as 1 over the function 1 over a to the power x, and it's just the same as 1 over a to the power of negative x. And therefore, using the rules of modifying the charts of the function when the argument is multiplied by -1, we can deduce that in this case the function is just flipped around the vertical axis, behaves just the same as the original one, but it grows as x approaches negative infinity, and it vanishes as x approaches positive infinity very, very rapidly. And it's an extremely valuable function as well. And I promise, just the same as I promised with the polynomials, I promise that we will use it quite often in our further discussions. Oh, by the way, since this function is monotonous, as is shown on the graph, we can compute its inverse function, and it's going to be logarithm. That's how the logarithmic function looks. Indeed, it's just the inverse of the exponent function. Nothing major, nothing super surprising or super counterintuitive. Just see the chart of it, appreciates that it grows very, very slowly, but it never tends to a limit. It grows all the way to infinity as x grows, as x approaches positive infinity, but it slows down very much. So there are some formulae for logarithms. They are simply derived from its definition, nothing particular to be said about it. You just better have a look at them and maybe write down, or maybe memorize, or maybe just remember when you need them that those formulae are summarized on this slide. And on this, we are done with the examples of the functions, and we are gonna transit to another big topic, which, well, first of all, is extremely important to all the things that will be discussed yet further, and secondly, it will significantly be grounded on the material that we just have discussed. So don't feel that the information that you just received is irrelevant or is not going to be used. No, it's not the case. All we learned now, we're going to use and we're going to need. So another topic is titled the derivative. So a derivative, as written here in our table of contents, is just essentially the velocity of the function, how fast it grows or how fast it changes as x changes. In order to study the velocity of a function, one has to give some increments to x. Let's just think how to study the velocity of the function's change under the change of its arguments. We have to give some increments to the arguments, give some increments to x, and we have to compute the difference between the new value of the function and the original one. However, this difference will depend on the increment. Well, let's normalize it then to make it less dependent on the increment. Let's compute the ratio of the increments of the function divided by the increments of the argument. And we see it here. So here is the function. We want to study the velocity of its growth at the points x0. We made some increments to x and came to the points x sub 1. we computed the increments of the function. It's these segments here. We computed the increments of the arguments. For the sake of normalization, we divided one by another. And what have we received? We have received the tangent of this angle here, the angle that connects the original points to the points where we ended up. All right, but still, this value is not really the characteristic of the behavior of the function in the points x0. It's in a certain way the averaged behavior within the whole this segment. So in order to make our study more precise, we choose a smaller increments to the argument, and we repeat the same procedure, and we end up with number tangents of phi 2. And if we want to make it yet more precise, we give yet a smaller increments to x, and we end up with the value of tangents for phi 3, and so on. And in order to study the rate of the function in the rate of the function's growth exactly at the points x0, we have to send the increments to infinity, send the increments to 0 while keeping track of those tangents values. And when we make the increments very, very small, infinitely small, when it tends to 0, the tangents values for phi 1, phi 2, phi 3 will approach the tangent of this phi asterisk angle, which is just the angle of the tangent line. Tangent straight line constructed at the points x0. And this will be the derivative. It's the instantaneous velocity of the function, instantaneous rate of its growth. And the formal definition of it is here, just as we discussed. It's the limit of the ratio of the increments of the function to the increments of the argument as the increments of the argument tends to 0. If the derivative of f of x at the points x0 exists and is finite, which is important, then f of x is obviously called differentiable at x0. The derivative can be computed at multiple different points, at any points where the function is differentiable, and then it itself will turn out to be a function, as shown on the next slide. So let's take the function f of x and construct another function v of x such that the value of v of x at each point is equal to the derivative of f of x computed at this point. This function will be denoted as f prime of x or df over dx. df, dx are just notations. It's not a real ratio, as just the mathematical formalism. As I said, it will be this function will represent, or can be interpreted as, the growth velocity, instantaneous velocity of the original function f of x. The greater the slope of the tangent line is, the faster the original function grows. If v of x is continuous, then f of x is said to be smooth, which relates to the obvious geometrical concept of smoothness of the function's chart. if the derivative is continuous, it means that there are no sharp turns of the chart of the original function f of x. Okay, so there is a theorem which is very important and which is very useful. The theorem is proved by Fermat, but it's obviously not the famous Fermat theorem, not the one that people struggled to prove for centuries. No, it's a simple Fermat's theorem. The theorem, like Fermat proved many theorems in his life. So this theorem says the following. If the function f of x is differentiable at the point x naught, and x naught is a local maximum or a local minimum, then the derivative of f computed at x naught is equal to 0. And this is a very powerful result for searching maxima and minima. During optimization procedures in all the machine learning approaches, like a lot everywhere in practical cases, one wants to compute some extremal values of a function and find where exactly, at which points in the domain of definition, the function reaches these extremal values, whether it's maxima or minima. It can be the maximum of a likelihood function, it can be the minimum of a loss function. It's very common for practical applications to seek the combination of variables, values of variables that satisfy the extremal values of the function. And for this, one can solve the equation, the derivative of the function equals to 0, finds x naught from this equation, and then check whether or not these points are really maxima or minima, or maybe they are something else. But anyways, constraining the search only to the roots of this equation significantly simplifies the search. You no longer need to screen through all possible values of x to search for minima and maxima. You have to constrain very significantly to a small subset of possible values of x, namely to those that satisfy this condition. And let's have a look how the derivative corresponds to its original function. So here the blue is the original function and the orange is the derivative. We see that when the original function grows, the derivative is positive. When it drops, the derivative is negative. When the original function grows with acceleration, the derivative grows. When the original function stops growing with acceleration and continues growing but slower and slower, as here, the derivative starts to drop. It's still positive because the original function is still growing, but that's already dropping. This behavior is symmetric here in this domain as well, because there is also a flip point here somewhere. All right, now let's discuss a little bit differentiability. This function is everywhere differentiable, and the derivative is nice, continuous, and everywhere defined. What are the examples of non-differentiable functions? Well, one is here. That's the function f of x that just is equal to the absolute value of x. And it equals to x when x is positive. It equals to negative x when x is negative. And those two branches are meet here at the origin. The derivative is defined here, it's just positive 1, and it's defined here, it is negative 1, but it's not defined at the origin. There is no limit of the ratio of the function's increments to the increments of the arguments. And this is the sharp turn, the angle, which indicates non-differentiability. Here, the curve itself, what is actually, what is this function? That's the function that is equal to the third power root of x when x is positive, and it's just symmetric when x is negative. And informally, it's just written here as x to the power 1 over 3. This branch is a cubic root, this branch is symmetric to the original one. And the curve itself is smooth. There are no angles, no sharp turns. But the derivative of this function is infinite at the origin, because the tangent line is vertical, and the corresponding value of the tangents of the angle is infinite. It's also an example of a non-differentiable function. A yet more bizarre example is Weierstrass function. Weierstrass is a very famous German mathematician of the 19th century, and he invented an example of a function that is everywhere continuous, but indifferentiable everywhere. And this is strange. Beforehand, previously, all mathematicians had thought that this singular behavior can occur just in isolated points if the function is everywhere continuous. But how can the function be everywhere continuous but never differentiable? I mean, one can imagine a function that is neither continuous nor differentiable at every point. That's Dirichlet function, which we already discussed in the beginning. The one that sends rational numbers into positive 1 and irrational numbers into 0. But it's discontinuous. How the function can be continuous and non-differentiable? Well, Weierstrass computed this example. The chart is approximate. It's impossible to draw the chart precisely, because every time you magnify an arbitrarily small area on this chart, an arbitrarily small segment, it will appear more and more broken, with more and more smaller peaks and wells. And such a behavior indeed causes non-differentiability. But one can prove that this function is is continuous. Such structures are called fractals. They have a number of interesting properties. We definitely will discuss these things a lot when we talk about random processes, stochastic processes. But even now, you can imagine that such a behavior occurs in the models of Brownian motion and diffusion. So a tiny particle suspended in a viscous media experiences continuous stochastic pushes and punches from the surrounding molecules, and it's not surprising that the mathematicians model these stochastic influences using those infinitely broken continuous functions. So keep this in mind. We will return to such patterns later throughout our course. Derivatives themselves have a pretty good feature. They can be computed using standard formulae. These formulae are here. For example, there is a known way to compute the derivative of a power function, the derivatives of all the trigonometric functions and their inverse, the derivative of an exponential function and the logarithm. And in general, there is a ultimate rule of computing the derivative of a sum of two functions with probably some constant weights. It's just going to be the weighted sum of the derivatives of each function, nothing more difficult. The computation of a derivative, differentiation, is a linear operation in this sense. It takes the weighted sum of the argument functions and it returns the weighted sum of the output. The derivative of a constant is zero, obviously, because it's constant, because constant doesn't change. Its velocity is zero by definition. The derivative of a product of two differentiable functions is here. The derivative of a ratio of two differentiable functions. The derivative of a composition of two functions is also here, and the derivative of an inverse. Now, if you are observant, you would notice that here I use the notation that I haven't previously introduced. This ln is nothing more than just the logarithm with a particular base. Is by definition just ln of x is a natural logarithm. It's the logarithm with a base e, where e is a particular number, it's an irrational number, and it's defined as the following limits. The limits with n tending to positive infinity of this construction here. Why it is so important? Well, it's a long story, but e is everywhere in mathematics. We will use it a lot. We will meet it a lot. For now, what we can pay attention to is that if we take the function a to the power x and we substitute a for e, we will discover that its derivative is again a to the power x. E to the power x, because ln of e equals to 1 by definition. So e to the power x after differentiation remains e to the power x. It's indistinguishable from its own derivative. Important property. It's important to keep in mind. So if we have an original function f of x, we could compute the next function v of x, which is the derivative of f of x. And we can subject this v of x to differentiation once again and compute the second order derivative, which would be denoted as f double prime of x, or it will be denoted as this d2f over dx squared. Again, it's just notation. That's not actual ratios. It's just the way how mathematicians write it. Similarly, the kth order derivative of f would be written as this or as this. Sometimes it's useful to think about the operation of the differentiation just as such, as a little machine to which you submit the input function and it returns its derivative. And then this little machine is called just d over dx. It's the operator of differentiation. And the kth order derivative of the function f is then can be formally written as the outcome of applying the operator of differentiation k times to the input function f, and it's also written as the kth power of the differentiation operator. This we also will use in later some later discussions, but not in the current lecture. And in the end, it's just a notation. Now, assume we computed this function here, dkf over dxk power, whatever. It's a function, it's the function of x, and we want to compute this function at a particular point. Then I prefer to use this notation. It's a little bit bulky, but it's crystal clear. What it says that this function, the kth order derivative of f, is computed at the point x that equals to x naught. It's the value of this function at x naught. Now, why on earth do we really need all these higher order derivatives? Well, the second derivative indicates the acceleration, as we already saw in one of the previous slides when I showed the graph of f of x and f prime of x on the same in the same frame of reference. The higher order derivatives are used for approximating functions, and that's what we are going to discuss next. Assume there is a function. In the current example, it's logarithm of x, and its chart is shown here with this blue line. Oh, and by the way, the scale on the y-axis is shrunk twice with respect to the scale, even 4 times with respect. No, sorry, twice. Yes, the y scale is shrunk twice regarding the x scale. Otherwise, just the graph would be too tall. So we have this blue curve, the function logarithm of x, and we want to approximate it. How do we approximate it? We want to compute it simpler. We want to use simpler formulae to approximately compute the value of this function in some neighborhoods of the points 1, for example. It was extremely useful in older times when computers were not there. So we can approximate it with a tangent line, which is shown here with this deep brown color, deep brown dashed line. It's the tangent line to the original function. It approximates the original function pretty well in this small neighborhoods of the points 1. And we know that the tangent line is strongly coupled to the derivative of a function in this point. But sometimes it's not precise enough. The function deviates from its tangent line too fast, and we want to compute it more precisely. For this, we introduce another derivative, and how to say? For this, we introduce another power. We don't examine the linear function anymore. We examine the second order polynomial with the second power of x in its formula. And this second order polynomial approximates the original function better than the straight line. However, it comes at a cost of the necessity to compute more derivatives, higher order derivatives. That's exactly the domain, or no, that's exactly the area of mathematics where the higher order derivatives meet polynomials. I told you that both are used for approximating functions, and here exactly how they are used. By computing higher and higher orders of the derivative in the given point, you get the coefficients of the polynomial functions of the higher and higher order that approximate your original function more and more precisely. Here is the first order polynomial, namely the straight line, that relies only on the first derivative, which approximates the original function, well, yeah, somehow. Here is the quadratic function that relies on two different derivatives, the first and the second one, and contains two powers of x in its formula, and it approximates the original function better. Here is the cubic approximation that contains the powers 1, 2, and 3, and the three orders of derivative. The fourth and fifth, and the more powers, the more derivatives we compute, the more powers in the approximation we're allowed to use, and the better our approximation is. However, this sequence of approximations converges not everywhere. It may converge everywhere on the real axis for some functions, for the exponent, for example, for the exponential function. However, for the logarithmic function, no matter how many summands you have in this approximation, you can approximate the original function only in the segment starting from 0 and going all the way to 2, not beyond it. In order to, because you see, so here the approximation converges, but outside this shaded area, the approximation diverges. Here the polynomials start facing into different direction. Here they are just, yeah, they just don't converge. And it's more or less obvious because all the polynomials are continuous functions, but logarithm is discontinuous. It tends to infinity when x tends to 0, or negative infinity, I should say. And here polynomial function grows slower than any, the logarithmic function grows slower than any polynomial, and it's impossible to approximate the logarithm with polynomials precisely at arbitrarily large distance from 0. Okay, so let's just appreciate it. We can use polynomials coupled with different derivatives for approximating arbitrary functions, well, differentiable functions, I should say. If you want to approximate it elsewhere beyond the area of convergence, then you have to take another point, let's say this point here, compute the original function precisely in this point somehow, and then expand this approximation in the neighborhood of this point. Yeah, only this way. Some points are allowed to be the reference points for the approximation. Some points are not, and this is depicted on the next slide. Oh, and by the way, this approximation with the polynomials is called Taylor series or Taylor expansion. Essentially, Taylor's theorem says that the infinite sum of these approximating terms eventually just converges to the function itself. You can approximate the function whatever precisely you want. Okay, so now let's return to the reference points. Here we used 1 as the reference point. Some other points for some functions may not be used, cannot be used as reference points. Here is the function that is defined by the formula f of x equals to 2 to the power of 1 over x squared minus 1 altogether in denominator. It's a pretty exotic function. And yes, by the way, the function is defined by this formula in the segments from -1 to 1, and beyond this segment it's just 0. Everywhere 0 except for this segment here. And it's a pretty exotic function. It has that property that there are 2 points that cannot be used for Taylor expansion as reference points, namely +1 and -1. Every derivative computed in these points will be 0. This function approaches 0 infinitely close, infinitely smoothly, infinitely quickly as x approaches one of these points. So no matter how many terms in Taylor expansion you will use, if you set one of these points as the reference points, the approximation will be always 0, everywhere 0. But if you use these points for the approximation, for example, the points that I'm just showing here, the 0, then you safely can compute the Taylor's approximation of any order you desire. That's it. Now, okay, we have been talking for a while about the derivatives, and I hope it's useful and I hope it's interesting. In order to complete and conclude today's topics, we have to discuss the operation that is inverse to computing derivative. We have to learn how to reconstruct the original function when its derivative is given. And that's going to be the last section of the lecture for today. This operation is called integration. And let's take a look first at the approximate computation of the derivative. What do we have here? This blue line is the original function f of x. The dashed gray line is its true derivative computed with a formula. And the dotted line, or this segmented line, is the approximate value of the derivative computed by using not limits of the ratios of increments, but the ratios of finite increments. We discretized x. We computed for every small increments of x the corresponding increments of f, and we just divided one by another, and we computed the approximation to the derivative of the function. It's not longer the Taylor approximation. Don't be confused. We just have finished the Taylor topic, and we don't talk more about it. It's another type of approximation. It's the approximation of the derivative by discretizing the x. Now, once we have this approximate formula, we can reconstruct the original values of f under the condition that the values of v, of its derivative, are given. How? Well, very simple. We just multiply both sides of this approximate equality by the denominator, and we group the summons in such a way that the f of x sub n plus 1 remains in the left parts of the equation and everything else is in the right parts of the equation. There's just arithmetic. There is nothing difficult. This formula directly follows from the upper one. And then what do we gain from here? Assume we know f of x sub 1. That's a very important requirement. So please just keep this in mind. So we'll talk later more about it. Assume we know f of x sub 1. And we know every value of v of x sub n. In every point x sub n, we know the value of v. What will we deduce using this formula? Well, since we know the f of x sub 1, we can compute f of x sub 2 using this formula. We can substitute f of x sub 1 here. The two values of x are known. This is known. Voila, we have f computed at the point x sub 2. Since we know f of x sub 2, we can compute f of x sub 3 using the same formula, and so on and so on. And by going interval by interval, we can approximately reconstruct the original function f using the given values of v of x sub n and the starting point. As shown here, the gray line is the same as the dashed gray line here. It's the derivative of the original function, which is now given to us. The orange line is the same as the blue line here. It is the original function which is not known yet, which we cannot use. And the segmented line is the approximation to the orange line that we computed using this function. All right? That's the main idea about integration. That's how integral is computed. Now the only final step to it is to transit to the limit and make the discrete approach here, a discrete approach presented here, continuous. Given the function v of x and two numbers, x naught and y naught, real numbers, requested finds the function f of x such that the derivative of f equals to v of x and the value of f evaluated at the point x naught is equal to y naught. And here is the protocol how to do it. First of all, we discretize the segment x naught to x with the points t sub n or sub k, whatever. T sub 1, T sub 2, ordered as shown here. Inside each smaller segment, T sub k to T sub k plus 1, we specify an arbitrary point R sub k, and we evaluate the function v in this point. So the blue curve here is the function v. These are the segments. This is the arbitrary points in which we evaluate this this function, and then we calculate the sum. This capital sigma means just the sum of these summands with k ranging from 0 to n minus 1. And where from do we have this sum? Well, it's just the same formula as was there in the previous slide. It's the formula approximating the reconstructed original function using the values of its derivative. Nothing else. It's just the same formula. With just points r sub k here being arbitrary, but not t sub k or whatever. But we will see how we'll deal with this. And now, actually, that's how we deal with this, with r sub k being not equal to t sub k. We shrink each small segment all the way to 0, times the maximal length of this segment to 0, while expanding the number of the segments. So we make the discretization more and more fine, more and more continuous, and in the limit, the value of the sum will approach the value of the original function f evaluated at the points x. The discretization is more and more precise. The approximation here is more and more precise. Based on what we learned in the previous slides, this will converge to the value of the function that we are searching for. And also geometrically, it's obvious that the value of this original function will be nothing else than the area below the curve v of x, restricted by the points x0 and x, if y0 equals to 0. If y0 is not equal to 0, then the evaluated f of x will be this area plus x0, plus y0, sorry. And at every discrete approximation step, as shown here, the s sub n, this value here, the approximate integral, is equal to the area of this fence, the discrete area below the curve. That's it. So, as I just said, from making the discretization more and more continuous, we eventually arrive at the limit. Is it really all I want to say? No, it's not. We still have to discuss a couple more properties of integration on the next slide. So first of all, the sequence s sub n must converge to the same number regardless of the specific discretization, specific splitting, the t sub k's, and regardless of the specific choice of r sub k's. We must be able to choose these guys whatever way, as long as it satisfies the ordering, and we demand that the approximations converge to the same number. Otherwise, the integral is not said to exist. It does not exist. Now, another important property, and it may be somewhat counterintuitive. Let's take a look at the function f of x plus a, where a is a constant. We differentiate it, and we find out that the derivative of a sum is the sum of derivatives, and the derivative of a constant is just 0. So the derivative of this beast here is just the derivative of the function f itself. And therefore, many different original functions f have the same v of x, have the same derivative. So by knowing only the v of x, one cannot reconstruct f of x exactly. One has to have the reference points x0 and y0. And it's just the same as I said 2 slides ago that f of x1 or f of x0, whatever that was, the origin point is extremely important. It's extremely important to select one of the possible original functions out of all the variety of functions that have the same derivative. By construction, so that's the property 2. The property 3. By construction, the integral is equal to the oriented area under the curve v of x up to a constant summand. We just discussed the constant summand. We discussed the area. What does it mean, the oriented area? It means that if v of x is negative, then the area consider it negative as well. Let's integrate this blue function here. That's our v now. We start from the condition that at this point the integral must be equal to 0 at this position which I show with the pointer, and then we'll start integrating it. So for example, let's choose this point x first. Let's compute the integral of the original function integral of this blue function at this point which I show with my pointer. And according to the protocol, it's going to be the area below this curve, between the curve and the horizontal axis. Cool. Now we make an increment to x and compute the integral in the new point x, and it's going to be the area in the whole previous shape. We keep computing the integral more and more, and we reach this point here, and okay, cool. So the area is now, so the integral is now this area, which is located to the left from the given x. But then something happens. Then v becomes negative. And within those sums, the v of r sub k will be subtracted now instead of being added, or they will be added, but they will be negative, and the integral will start dropping, just the same as we showed in the graph where the original function and its derivative are depicted on the same plot. When the derivative is negative, the original function starts dropping. And that's what we see here. When the derivative is negative, its integral is dropping, which corresponds to the negative area, this negative area here. Cool, I think this is understood. Now the fourth property from this slide, it's not a property, it's actually a notation. The integral is written as follows, as y0 plus the integral sign, which is inherited from that sigma, is just the evolution of the sigma, so to say. That it's the sigma subjected to natural selection. It's like prehistoric apes that evolved into a nice and slim and fit Hollywood star. So it's a integral sign. The integration is conducted over the variable t, and t is that variable that ranges from the original points all the way to x. It's not x, which is fixed for now. It's the variable that originates from those t sub k's here in the discretization. So t equals from x0 to x, v of t dt. dt is a notation that is inherited from t sub k plus 1 minus t sub k, but right now is just the way how the integral is written. It doesn't quite mean a lot. Rather, it's just an element of the integral sign, I should say. And we pay attention that the arguments of the resulting function, the argument that is sitting here in the formula for the integral is here, is at the upper boundary of integration. Let's put it, let's appreciate it. The variable is not here, actually, it's here. However, this notation has a bit of modification. So here is the modification, the property number 5. You may often see the undefined integral notation written as follows. F of x equals to the integral sign itself without boundaries, v of x dx with the same variable here and here. What does it mean? It denotes the entire set of functions whose derivative is equal to v of x, with x0 and y0 being not specified. So f of x is not a single function, it's all functions that satisfy the property f prime of x equals to v of x. All such functions are different, all such functions are different from each other by a constant summand, and only by constant summands. The property number 6, again, it's not a property, it's a comment. For the strict theory, see the term, the fundamental theorem of calculus. It's written in every calculus textbook, and it dates down to Newton, Isaac Newton, and Gottfried Leibniz. Newton in the United Kingdom and Leibniz in Germany. So the property number 7. Okay, sorry, let's speed up a little bit. The property number 7. There are no universal formulae for integration. Oh, that's important. That's an important thing. Previously, for the differentiation, we specifically claimed that there is a way to differentiate any function, because there is a huge toolbox that allows to differentiate sums and products and compositions and different combinations of different functions. There is a formula for differentiating sines and exponents and whatever you want, but it's not the case for integrals. In fact, for many integrals, it's proven that they just cannot be expressed in those regular functions, in those like common functions that we have, that we know. Well, sometimes numeric integration, approximate integration is sufficient. One can just compute the integral using a computer, approximately. Sometimes people just define the integrals of certain functions as another elementary function and add them to their vocabulary of elementary functions, whatever. So, for example, the Gaussian function, e to the power negative x squared, doesn't have an integral that would be expressible in elementary functions in like powers and sines and exponents, but it's very widely used, and for this they just generate a particular notation for it using the error function. It's called error function, and the properties of this integral are known, the behavior is known, the values are already computed and stored in tables. So it's just the same as expanding the vocabulary of elementary functions. And those functions are called special functions sometimes. Now, the property number 8. If a function is differentiable, it means that it is continuous. If it is continuous, it implies that it is integrable. Well, I shouldn't say means. If the function is differentiable, it implies that it is continuous. If it's continuous, it implies that it is integrable. But these relations are generally not satisfied the other way. So there are functions whom you can integrate, but they are discontinuous. And also there are functions that are continuous but not differentiable, as we saw at the example with the absolute value function, which is continuous, yes, but it has that sharp angle, sharp corner at the origin, which makes it non-differentiable. Finally, the property 9. Some functions are not integrable, but are very much needed to be integrated. And you know that human beings are very elaborate in breaking rules when something is impossible to do, but it's very needed to be done. And they invented alternative operators to integration, which have broader domains of applicability, something that coincides with a regular integral when you talk about just regular integrable functions, but can act on a broader set of functions. Like, for example, Lebesgue integral can integrate Dirichlet functions. They can integrate the Dirichlet function and similar functions. And Ito integral can integrate something like Brownian motion path, the functions like Weierstrass functions. We will discuss these things. We will discuss the Ito integral for sure when we talk about stochastic processes, and I think we will discuss Lebesgue integral a little bit too, but not in this lecture. This lecture is almost over now. Let's discuss some minor points, and after that it will be done. So the last points I want to touch here is so-called improper integral. Let's pay attention to this blue curve. Let's integrate it. Let's integrate it starting from this 0.5. Let x naught be 0.5 and y naught be this value. Sorry. Let's x naught be here and y naught be here, approximately 0.9. We integrate it, and the integral at the point 1 will follow this orange curve. It will have this value, 0.95 or whatever. The integral at the points 1.5 will be equal to 0.99 or something like this, and so on. While moving x farther and farther to positive infinity, we observe that the value for integral tends to a certain limit. If we started from 0.9 at 0.5, let's integrate it backwards. Then we will be subtracting the area below this curve, because t sub k plus 1 minus t sub k will be negative at this point. And we will subtract first this area, then this area, then a greater area. We will keep subtracting the area constrained by this diverging curve that tends to infinity. But again, we will hit just a finite number, and we will approach to 0 at origin. This curve, the blue curve, has an interesting property. Although it tends to infinity as x tends to 0, and it tends to 0 as x tends to infinity, the area below it, the area constrained by the curve and the axis, is actually finite. Not every curve satisfies such property, but if the curve does, then one says that it has an improper integral, and it's denoted like this: an integral over x ranging from a to positive infinity of the function f of x dx. What it means? It means the limit of the integral over x ranging from a to b of f of x dx, while b is tending to positive infinity. And by the way, the specific example shown here, the blue curve, is the so-called Weibull probability distribution function. Which properties does the improper integral have? I love English language, really. There's so much of opportunity to juggle the words like this. Properties of an improper integral. It's very poetic. It sounds very poetic. Like, not every function that tends to infinity at a point has an improper integral there. For example, 1 over x does diverge as x tends to 0, but it doesn't have an improper integral. But 1 over x to the power a does have an improper integral if a is confined between 0 and 1. The same thing holds for the limits at infinity. 1 over x has no improper integral as x grows unboundedly, but 1 over x to the power a does have an improper integral if a is greater than 1. All right, that's, I think, all I want to discuss today. As I said, there are going to be many more talks, and they will be gradually approaching biology, biological applications. First talks will be, I think, the same strictly mathematical as the current one. However, once we learn the ground theory, and once we familiarize ourselves with the terminology, we can proceed with solving and discussing the tasks that originate from natural phenomena better. On this, look, I congratulate you. You did a great job by staying here with me. If my talk was not that understandable, don't hesitate to reach me privately or to write a comments for this presentation, for this video. I'm wishing you all the best, and see you next time at the next lecture. Take care, everybody.